Now see PYQ, previous year questions from the chapter electronic devices. See the first question, a full wave rectifier circuit consists of two PN junction diodes, a center tapped transformer, capacitor and a load resistance. Which of these components remove the AC ripple from rectified output? See, it is the capacitor. Okay, and it is called a filter circuit. Next, the incorrect statement about the property of a Zener diode. P and N regions of Zener diode are heavily doped. Zener voltage remains constant at breakdown. It is designed to operate under reverse bias. Depletion region formed is very wide. So, this is a wrong statement. Next, see in the given circuit 1, 2 and 3, the potential drop across the two PN junctions are equal. Here both the PN junctions are forward biased, so the voltage across both the junctions will be the same. Here one is forward biased and the other is reverse biased, so the voltage across the two junctions will be different. Here both are forward biased, again the voltage across the two will be the same. So 1 and 3, both the circuits 1 and 3. Okay. Now see in half wave rectification, if the input frequency is 60 Hz, then the output frequency is also 60 Hz. See in input, see this is one cycle, okay, and in output, see this much is one cycle. So in each time when input make one cycle, output also make one cycle in a half wave rectifier. So the frequency of input is 60 Hz, then the output frequency also will be 60 Hz. Then which of the following represents forward bias diodes? See, this is P side and this is N side. See, the potential at P side must be more than the potential at N side for the PN junction to be forward biased. Okay. See, here we have -4 on the P side and -3 on the N side. So the potential at P side is smaller, so it is not forward biased. Here we have -2 at P side and +2 at N side. This is also reverse biased. Here we have 3 at P side and 5 at N side. Again it is reverse biased. Here we have 0 at P side, -2 at N side. So this is forward biased. Consider the junction diode as ideal, means when forward biased it will act as a short circuit. That is what's meant by an ideal diode. Okay, the value of the current through AB is, here we have +4 and here we have -6 volt as potential. Okay, the diode is forward biased, as it is an ideal diode, it will act as a short circuit. So the potential difference across the 1 kilo ohm resistance will be 4 minus -6. Okay, so that is 10 raised to -2 ampere. 10 raised to -2 ampere. Next, see if in a PN junction a square input signal of 10 volt is applied as shown, then the output across RL will be. See, here, see the voltage is negative. So diode will be reverse biased, so output will be 0. Okay, here voltage is positive. Diode will be forward biased and output also will be 5 volt. Again, see here voltage is negative, diode will be reverse biased. So 0, 5, then 0 again. Okay, output must be as 0, 5, then 0 again. Here 0, 10 and 0. Okay, here -5, 0, no. Here 0, 5 and 0 again. So this must be the correct outputs. Next, see in the given figure, a diode capital D is connected to an external resistance 100 ohm and EMF of 3.5 volt. If the barrier potential developed across the diode is 0.5, the current in the circuit will be. See, the total voltage is 3.5, of which 0.5 will be dropped across the diodes. The remaining 3 will appear across the resistor. So the voltage across the resistor is 3 volt and the current through it is given by I equal to 3 divided by resistance 100 ohm. So it is 30 milliampere. 30 milliampere. Next, in an n-type semiconductor, which of the following statements is true? Electrons are majority carriers and pentavalent atoms are dopants. That is true. Okay. Next, in an unbiased PN junction, holes diffuse from P region to N region because, see the potential difference across the PN junction, that's wrong. The attraction of free electrons in the N region, that's wrong. The higher hole concentration in P region than in N region, that is true. Okay. Two ideal diodes are connected to a battery as shown in the circuit. The current supplied by the battery is, see, this is the positive pole, so this diode will be reverse biased and this will be forward biased. So the electric current will be like this. Okay, electric current will be like this. There will not be any current through this middle branch. D2 is reverse biased. So this 20 ohm resistor will not come in the circuit. So that branch can be eliminated. Okay. Now see, we have a 5 volt and the only resistor in the circuit is 10 ohm. So the current will be 5 by 10 or 0.5 ampere. Right. Now in the following figure, the diodes which are forward biased. See the first one. See the higher potential is on P side. So it is forward biased. Here we have minus 10 at P side and 0 at N side. So this is reverse biased because see at P side the potential is lower compared to that on N side. Okay, here we have a minus 2 at N side and minus 5 higher voltage at P side. So this is forward biased. Here 0 at P side and plus 5 at N side. So this is reverse biased. So the forward biased diodes are A and C. Okay, here it is C and A. Right. Now a Zener diode having breakdown voltage equal to 15 volt is used in a voltage regulator circuit shown in figure. The current through it is, see the total voltage here it is 20 volt. Okay, of which the voltage across the diode is 15. So the remaining 5 volt will be dropped across this 250 ohm. Okay. Now see this resistor, this is connected across the diode. So the voltage across this resistor will be same as the voltage across the diode, and that is 15 volt. So here we have 1 kilo ohm. So the current through this resistor will be 15 volt by 1 kilo ohm, that is 15 milliampere. Okay. Here the voltage is 5 volt and the resistance is 250 ohm. Okay. So the current through this resistor will be 5 by 250. Okay. 5 by 250. Multiply both the numerator and denominator by 4. You will get 4 into 5, 20 by 1000 or 20 milliampere. So children, so the current through this is 20 milliampere. Of that 20 milliampere, 15 milliampere will be going like this, and the remaining 5 milliampere will be through the Zener diodes. Okay, so 5 milliampere through the Zener diodes. Zener diode is used for stabilization, voltage stabilization. If a full wave rectifier circuit is operating from 50 Hz means the fundamental frequency in the ripple will be, see, for the input wave this is 1 cycle, and for the output see this itself is a cycle. So by the time input makes 1 complete cycle, this output will make 2 cycles. So the frequency of the output will be twice the frequency of input in a full wave rectifier. Okay, so output must be of frequency 100 Hz. A DC battery of V volt is connected to a series combination of a resistor capital R and an ideal diode capital D as shown in figure below. The potential difference across R. See, 2V when diode is forward biased, 0 when diode is forward biased, V when diode is forward biased. Okay. Now see, an alternating current can be converted into direct current by rectifier. Okay. Now a piece of copper, that is a conductor, and other of germanium are cooled. Okay, when cooled, the resistance of germanium will increase and the resistance of copper will decrease. Okay, resistance of copper will increase, that's wrong. Resistance of copper will decrease and that of germanium will increase, that is the correct option. Now for the following logic circuit, the truth table is, See, this is an inverter, so here we will get A complement. This is another inverter, here we will get B complement. Now this A complement and B complement are given to a NAND gate. Okay, NAND gate, so output will be A or B. Means the output will be 0 only when both the inputs are zeros. Output will be 0 only when both the inputs are zeros. Okay, so this must be the correct option, this one. Okay, output is 0 only when both the inputs are zeros. Next, see, identify the equivalent logic gate represented by the given circuit. Children, see, this bulb will glow. See, when either of these two switches is in the on position, when A or B is 1, or when the switch A or B is in the on position, that bulb will glow. Means we will get an output when A or B is 1. Means it must represent an OR gate. Must represent an OR gate. Now children, here we have a NAND gate. See, the two inputs are A and B, so the output will be AB complement. Now see that A is given to the input of an inverter, so here we will get the A complement, and here we have B, so the output will be A complement B whole complement. This is an AND gate. Okay, so the output will be A complement or B complement. By De Morgan's theorem, this AB whole complement can be written like this, and this A complement B whole complement can be written like this. Okay, and this will be equal to B complement. So the output will be always the complement of B. See, when you consider this option, see here we have output same as B. Okay, so that should not be the correct option. And see, here here B is 0, output is 1. Here B is 1, output is 0. Here B is 0, output is 1. Here B is 1, output is 0. So this must be the correct option. Means output is always B complement. Okay. Now let's see what we have next. Which of the following gate is called a universal gate? NAND gate and NOR gate are called universal gates. Here we have NAND gates. Now for the given circuit, the input digital signals are applied at the terminals A, B and C. What would be the output at the terminal Y? See, here the output will be AB and here the output will be BC whole complement. Okay, so here we will get AB or B complement or C complement. Okay, now see, if B is 0, if B is 0, B complement will be 1. See, if B is 0, B complement will be 1. And the output will be 1 irrespective of the status of the other variables. When C is 0, see, when C is 0, C complement will be 1. And the output will be 1 irrespective of the status of other variables. Okay, now see, when B or C is 0, see, during this interval B is 0, output must be 1. Okay, and see, during this interval C is 0, so output must be 1. Okay, during this interval B is 0, so output must be 1. So the output must be 1 throughout. Okay, so 1 means 5. Okay, so this must be the correct option. Okay, now see here, see, when A or B is kept open, when A or B is kept open, there won't be current through this branch. Okay, then there will be current through this branch and the bulb will glow. So the bulb will not glow or bulb will be switched off only when both the switches are in their on position. Okay, so we will get an output 0, means bulb will be switched off only when both A and B are 1. So output is 0 only when both A and B are 1. So it must be a NAND gate. Okay, it must be a NAND gate. This one. Now see, here the bulb will not glow when A or B, when the switches A or B are in on position. bulb will not glow, okay, when A or B are in their on position. So bulb will glow only when both A and B are in their off position. So the output will be 1 only when both A and B are 0. Means it is a NOR gate. It is a NOR gate. Now here we have another logic circuit. In the combination of the following gates, the output Y can be written in terms of inputs. See, this is A B complement plus A complement B, and this is an exclusive OR function. Exclusive OR function. A B complement or A complement B. This is called exclusive OR function. Exclusive OR function. Okay, and there is a gate called exclusive OR gate, and its logic symbol is like this. Okay, this is exclusive OR gate. This is A, this is B, and here A exclusive OR is represented like this. A XOR B. Okay, output is 1 when the two inputs are at the opposite levels. Okay, output is 1 when the two inputs are at the opposite levels. Now let's see next. This is here we have A and B at the inputs, and in the output we have A or B whole complement, means it is a NOR gate. NOR gate. Okay. Now see, here we have to get 1 for the following circuit. See, the correct choice is, see, this is a AND gate. So in order to get an output 1, this C should be 1. Okay, C should be 1. Then only we will get an output 1. Okay, C is 1 only in this option. Okay. Now let's see what we have next. Here we have A and B as inputs, and ultimately output is AB. So it must be an AND gate. Right? Next, see, this is this we have done earlier. See, the output from a NAND gate is divided into 2 parallel and fed to another NAND gate. Resulting gate will be AND gates. AND gates. Okay. So when A and B are given, here we will get AB whole complement. Okay, this will act as an inverter. Finally, we will get AB. So it acts as AND gates. Now output X of the logic circuit shown in the figure will be, see, this is AB complement, and the second NAND gate will act as an inverter. Finally, we will get AB. So X equal to AB. Okay. Now see, symbolic representation of 4 logic gate are shown. See, the first one is an OR gate, second one is AND gate, third is an inverter, and finally we have a NAND gates. Okay, we have to identify AND is second, NAND is fourth, and NOT is third. Second, 4, third. Second, 4, and third. This one. Okay. Now the circuit, the first one is a NOR gate, then NAND gate, and it acts as an inverter. So the output here will be OR, and this is a NOT gate. So the final output will be NOR. This one, NOR. In the following circuit, the output Y for all possible inputs A and B is expressed by the truth table. This is an OR gate, and this is an inverter. So this combination acts as an OR gate, and output will be 0 only when both the inputs are zeros. Output is 0 only when both the inputs are zeros. Means this must be the correct option. The output of OR gate is 1 if either input is 0, if both inputs are 0, if either or both inputs are 1. Okay. Which of the following gets will have an output of 1? Here the output will be 0, and here the output will be 0. Here the output will be 1. Okay, so C. Okay, this must be the correct option. Right?